Hello, my name is Juan de Dios Ruiz, and the title of my project is Turquoise Stabilization from Child Grade to Gem. Thank you, Lord, for coming to see me. Well, let's begin.
All of the information will be here on this PowerPoint presentation that I made. As I said before, my name is Juan de Dios Ruiz Jaramillo. I come from the UANL, Facultad de Ciencias Químicas. My director is PhD Tomás Constantino Hernández, and my co-director is PhD Francisco Javier Garza. Well, let's begin. I think it's good to mention that this project was requested by someone outside the university. Mr. Carlo Muñiz from the ACMT Enterprise contacted our working to resolve the issue regarding of his turquoise. He wants the child grade turquoise to be graded to have better tenacity and hardness so it can be sold better. We accepted the project and these are the results. But before I show them, let's start talking about turquoise. Well, turquoise it is a phosphate of aluminum and copper. Its cryptocrystalline structure is what gives its porosity, and in the region between northwestern Mexico and the southwestern United States, turquoise stands out as an important mineral. Currently, it is mostly mined in China, Iran, Mexico, Tibet, and the United States. But for now, let's talk about Mexico and the United States only. There are deposits of turquoise in California, Nevada, Arizona, Colorado, New Mexico, in the United States, and Baja California Norte, Sonora, and Chihuahua in Mexico. For the turquoise mined, approximately 5% is gem grade turquoise, while the remaining 95% is chalk grade turquoise. But what is the difference between chalk grade and gem grade? First, we need to clarify that they have the same chemical form like crystalline structure, but they have different density, hardness, and toughness, and price. The gem grade has higher density, hardness, and toughness. Talking about the price, we have to talk about turquoise quality index. You see, the set of these parameters give a rating of 100, that is the maximum, and the minimum, will be 1. There are hardness, composition, disponibility, matrix, enhancement type, cut, color, and size. The only ones that we can manipulate and can work with are the hardness and enhancement type. This graph shows the relation between the quality and the price, and yes, if the quality is high, then also the price. There is a very large price difference, so the miners, to raise profits, have tried to improve the colors and durability of chalk grade turquoise, as the only use for turquoise nowadays is ornamental only. For a chalk grade turquoise, we can only have up to 10 USD maximum. The minimum will be 0.01 cents of a dollar. And for a gem grade turquoise, will be minimum 50 and maximum of 1000 USD. That's a high difference. Talking about the background, there were different methods to enhance the quality of turquoise: the wax treatment, plastic stabilization, and dye. Although the first two treatments improve color and durability by filling the pores of the turquoise, they have the disadvantage of being non-permanent and vulnerable to heat. Dyeing is also not viable because turquoise color could fade easily. These methods might not provide the characteristics sought in a gem grade turquoise. On the other hand, the Zachary process, developed in the late 80s, not only improves the color and durability of turquoise, but also does not cause oxidation or discoloration, making it the better method for stabilizing chalk grade turquoise. To increase profit and reduce waste, the miners choose to send the chalk grade turquoise mineral to the United States to turning it a gem to a specific enterprise. Although it is the best method to stabilize turquoise, the drawback is the lack of reference due to the fact that this is an industrial secret. The Zachary process includes general treatment to improve durability, surface treatment to enhance color, and general surface treatment to improve color and durability at the same time. In order to propose a turquoise stabilization process, we need to look indirectly at what the Zachary process is about. In 2008, Kwon et al. Analyzed the characteristics of a turquoise treated by the Zachary process and compared the result to a real untreated turquoise. The results suggested that the properties are very similar to those of natural turquoise, and it is very difficult to distinguish them by a general method of gemstone identification. The only way to differentiate treated turquoise from pure turquoise is through chemical dispersive X-ray fluorescences analysis. Sorry. Also, the two more important characteristics is that they confirm in the Zachary process turquoise is that there is a silica presence and hydrogen, but it's not identified. Now I will show you these items and the respective price, only for you to try to guess its value, okay? Rosa des Benz, a bracelet by Dior, Jacob & Co. turquoise diamond and Saboriti? I'm not sure. Oyster Perpetual by Rolex, and Patek Philippe Nautilus. You see, the bracelet by Dior is worth 17,600 USD new. The Jacob & Co. are 6,500 USD and they were used on eBay. The Oyster Perpetual are 11,915 USD new, and the Patek Philippe and $52,635. Yes, is rather expensive. Yes, these articles are used to show you that turquoise has relevance even today. The fact of improving turquoise allows it to be used to make this kind of accessories. Chalk grade cannot be used; it's only gem grade, so it's a way to use or treated turquoise. Now let's talk about experimental procedure. The first step is to make silica salt gel. So we will add 0.5 mol of tetraethyl orthosilicate, 2 moles of ethanol, then add 5 moles of water by the rate of 1 milliliter per minute. Then after that we will adjust the pH to 3 with using nitric acid and keep agitating during 6 hours at 60 degrees Celsius. Now the second step could be turquoise selection. Mostly of the turquoise selected has to be at least 2 centimeters in diameter, okay? Then we will make a pore size measurement and we will separate 2 turquoise, okay? In the first, we will not use the salt gel, the silica salt gel, okay? But the second one, we will put under 200 milliliters of silica salt gel plus 0 minutes of low vacuum. Then we will heat it between 90 and 88 degrees Celsius for 24 hours. Then we have these two kind of turquoises, and then the next step will be the reinforcement with opticon resin at low vacuum. Turquoise samples with and without silica will be strengthened with polymer under vacuum. The reinforcement depends on the pore size. Studying its correlation will be part of our research. That's the reason for the bet in the last in this part. While our goal is to stabilize turquoise, some of the research will be part of our results. Then, after the reinforcement, some of the turquoise will be cured on the ultrasound equipment, and another turquoises will be cured without ultrasound. And in the end, we will have 4 kinds of turquoise with silica, ultrasonically cured resin, and well, the other parts who doesn't have these properties. Okay, these are mostly the 4 types of turquoise that we will work with. Now let's begin with the results. First, let me show you about the turquoises that we received. There were a lot. All of them were different sizes. They have little hardness, yes, it's normal, and they have an unknown orange phase. This is 4 samples to realize an X-ray diffraction. As you can see, there are not the same amount of this orange phase that we can see here. Being that the turquoise is not pure, we seek to characterize the orange phase that it can be observed in the images. The first test that we will do is to detect is to detect this orange phase using X-ray diffraction. Now, here are the specters. All spectra were compared to the American mineralogist crystal structure database record, being all with triclinic structure. As you can see, as this orange phase increases, both noise and fluorescence increase also. This, combined with the elemental analysis, corroborate the presence of iron 3 oxides. It's good to know. The result of the pore size of the turquoise determined through the absorption-desorption isotherm turned out to be type 4 according to the Brunauer, Deming and Teller or BDDT classification. As there is no pore blockage, it is assumed that there is a three-dimensional network of interconnected pores, or, in other words, is also mesoporous. This information is important for us so that we can later carry out a study of the relationship between the pores and the resin in our research team. Okay? Next, let's talk about the stabilization turquoises. The turquoise that we can see up is chalk gray turquoise without any treatment, and the turquoise that is below that is after the treatment. Hardness and tenacity test. Finally, there are the physical results of 7 turquoise samples. I have to clarify that these results are for ultrasonically cured and non-silica turquoise only. The measurements of the other turquoises are pending. But well, let's begin. The frequency corresponds to the one chosen for the ultrasound during setting. The amplitude refers to the average pore size for each sample. And only the Vickers hardness and Sharpie type impact values remain. The hardness values are comparable to those of polymer fiber reinforced zirconia or PRC, which is a ceramic matrix composite for a mechanical use, and the toughness and the tenacity values provided by the Sharpie impact are similar to those of low alloy steels. The results are so good for us to show you, and also for Mr. Carlos, claro. Conclusion: the stability of chalk gray turquoise is revealed through the application of optical resin. The absorption-desorption curves obey its initial mesoporosity, offering an advantage by acting as interconnected tunnels that facilitates fluidity and wetting. Ultrasound emerged as an alternative energy source, eliminating the need of heat and catalysis. Hardness values, including the minimum, provide the ability to polish the stabilized turquoise akin to its gem-grade counterpart. Notably, it's worth mentioning that optical resin doesn't color the turquoise, it merely imparts a lustrous finish. Special thanks to my director PhD Francisco and PhD Tomas, and special thanks to Mr. Carlos Muñiz, as he provided all the turquoise and for trusting our team for this project. These are my references, and that will be the end of my presentation.
And that will be all of my presentation. Thank you a lot for attending. Here I will leave the emails of me and my directors. If you have any questions or any regarding matter, please feel free to reach. And well, that will be all. Thank you a lot. Enjoy the rest of Congress and have a nice day. Hasta luego.